In this last video, I want to talk a little more precisely about how we are going to use technology to determine these coefficients and some of the technological problems that we may encounter. So what I have here is what we covered in the last video. In building f of 6, we were looking at these sums of having 5 bags at the previous step, 3 bags at the previous step, or 1 bag at the previous step. And then we needed to determine these coefficients. And the coefficients were important for us to determine, well, how would I have gotten 5 bags? Well, it must have come from 4 at the previous step. How would I have gotten 3 bags? How would I have gotten 1 bag? And in order to determine these coefficients, we looked one step prior to this number of bags. But something interesting is that the only thing we needed to know to determine these coefficients was A, what the coefficients were at the previous stage. Those were the numbers highlighted in blue. And then we needed to do some arithmetic with our binomial coefficients, and those seem to matter as to what stage we were at. So let's be a little bit more precise here. I could generate something like this that looks a little bit more low tech but has all of the data that I might need by having the day number as my row here, and then I can use the columns to help me to figure out what the binomial coefficients ought to be. So for example, when I'm figuring out what should go in the 0th column on stage 5, I might want to be looking at a 4, choose a 0 for my coefficient, and then put that here. When I'm going to something like a 10, I know that it needs to be a 1 times some sort of binomial coefficient plus a 4 times some other sort of binomial coefficient, and I can look to the pattern on the binomial coefficients to figure out exactly what those numbers should be. And similarly from the 5. I know that my coefficients will be a 1 and a 4 and a sum of those things, but in order to figure out what they need to be, I need to pay attention to the red patterns here. So using a handful of simple formulas in Excel, things that are talking about the combin function and maybe an if-else function to talk about if I want to have a 0 here or not. I've put zeros in all of the odd different positions. We should be able to come up with a formula in Excel that will generate these rows just by dragging and dropping. So that's one thing that we could do. However, we are going to run into some computational issues. For one, the number of possible arrangements grows very, very quickly. We have done all of our examples here in these first couple of cases, which are pretty reasonable to draw out by hand, but we're going to lose our ability to do that at a very fast rate. And unfortunately, by the time we even get to day 14, we should be looking at approximately 2 billion possible configurations. And so unless you're using something like Mathematica that has infinite precision, you are going to run out of storage space in the values that you're using. So that's going to be an issue in almost any programming language. So let's change the question a little bit. Let's not ask for the total number of bags here, but let's pick something. Let's pick some sort of number, maybe close to the integer maximum in a programming language, and then pick a number that's sort of special. And I'll go into that more in the next slide. And instead of asking for the total number of arrangements, maybe let's just ask for the total number of arrangements modulo this particular m. That will make it so that we don't have to worry about overflow issues, and we can extend past the first 14 or so examples. However, this is going to require a little bit of gymnastics for us. Almost any programming language will have a built-in mechanism for taking binomial coefficients or doing an n choose k of some sort, but you're going to have the same overflow issues if you use that built-in function. They're not going to be equipped to handle it. So we're going to have to use the definition of the binomial coefficient and some things that we know about our special modulus in order to write our own binomial coefficient function. Now, what I mean by that is n factorial gets really big really quickly. If I'm looking at something like 14, 15 factorial, I'm going to have some overflow issues. And there's a very easy way to solve this given that we're modding, which is we can compute a factorial with a little for loop, and we can just mod every time we multiply. And that'll make sure that that numerator never gets very big. And the same thing with the factorials that we have in the denominator. However, if we're modding as we go, modding the numerator and modding the values in the denominator, we might get into a point where things don't make a whole lot of sense. For example, if I were trying to compute something like 8 choose 5, I might have difficulty with that because working modulo 13 for a small example, 8 factorial is 7, which is prime. When you look at 5 factorial mod 13 and 3 factorial mod 13, I get a 3 and a 6. And so we have to think about what does it even mean to say compute 7 divided by 18 mod 13. We don't normally mod fractions, and so we need to think about that a little further. So the little bit of gymnastics that we need is that this particular m value is prime, and prime numbers are like magic. There's going to be a special number called an inverse for every number that could make sense in these computations. And what inverses are numbers so that when you multiply them together, you don't get 1, but you get something that when you mod it by 13, or mod it by the modulus, it's equivalent to 1. And so that's good enough for our sake. So what we're going to need to do is work with our computer programs to compute inverses for things like the 3 and the 6, and not just use the insight provided in this video. We're going to need to write a computer program that can compute these inverses and then replace a division with a multiplication. Just like instead of dividing by 3, you might multiply by a third. Instead of dividing by 3 here, we'll multiply by 3's inverse. So the setup is do the multiplications modding as you go so the numbers don't get very big. Then you'll need to compute inverses for these values that you get and change this division into a threefold multiplication.